In the 1960s, as high-speed rail travel started to revive the fortunes of the Iron Way, the national train operators of the world scrambled to implement their own methods of making rail transportation a viable alternative once again to the likes of motorways and domestic air travel. While mainland Europe busied itself with the early development of dedicated high-speed lines as per the TGV, and Great Britain sought to implement tilting technology by way of the ill-fated advanced passenger train, the first venture of the United States into high-speed train travel would be with the Budd Metroliner, a highly ambitious attempt to provide the Northeast Corridor between Washington, D.C. and New York with 160-mile-an-hour electric rail cars. Sadly, the Budd Metroliner was a concept doomed from the start, as through a lack of investment, an absence of government interest, a restrictive timescale, outdated infrastructure, and a severe deficit in terms of technological knowledge by the rail manufacturing company, the intention of creating America's answer to the Shinkansen would fail to be solved, and the Metroliner would become but a footnote of rail travel's fight back against cars and airlines. The Budd Metroliner was essentially a long-standing answer to the question of declining railway popularity during the mid-20th century, as with the widespread adoption of faster, multi-lane highways and domestic air transport, the once dominant place of the American railroad atop the market for cross-country travel was rapidly eroded, with prestigious expresses and vital local corridors all being stripped of their passenger numbers. In some instances, various railroad companies were quick to note the threat that domestic air travel and highways posed to their market share, and undertook ambitious experiments as to how train operations could be made both affordable to operate but also comparable in speed and efficiency, especially when compared to cars. The Budd Rail Diesel Car, or RDC, was one such method, as introduced from 1949, and comprised a single stainless steel self-propelled coach that could work in multiple and would replace the use of locomotive and coaches on lower-capacity branch lines across the northeast United States, putting up a stiff fight against the car on various regional workings. However, long-distance trains, such as the 20th Century Limited and the Super Chief, were completely at the mercy of domestic air travel, as the arrival of turbine-powered airliners, such as the Vickers Viscount and the Boeing 727, meant a journey that had previously taken a train either 1 or more days to complete could now be done in a matter of hours, and the railroad companies had no viable means to combat such a stark difference in speed. This did, however, lead to some outlandish ways to fight back against airliners, with 1966 seeing the New York Central Railroad take a leaf from the book of jet airliners by fitting an RDC car with General Electric J47-19 boosted jet engines from the Convair B-36 Peacemaker strategic bomber, creating the M497 Black Beetle, which was able to attain a record top speed of 183 miles an hour, but was by no means a practical option for routine work. A solution presented itself, though, during 1964, when Japan inaugurated its high-speed Shinkansen line between Tokyo and Osaka, the world's first dedicated high-speed railway that was both capable of achieving speeds of over 130 miles an hour, but was also completely divorced infrastructurally from other railway operations, thereby creating a self-contained high-speed system that did not need to contend with slow-moving freight trains or commuter services. The arrival of the Shinkansen prompted figures in the American government to act in order to save the railroad industry, with Senator Claiborne Pell and President Lyndon B. Johnson working to develop legislation for a high-speed demonstration project in the United States, with late 1965 seeing Congress pass the High-Speed Ground Transportation Act. This act authorized $90 million of state funds for the creation of an Office of High-Speed Ground Transportation, which would support the research, development, and construction of a high-speed demonstration project on the Northeast Corridor, the primary main line between Washington, D.C., New York, and Boston, this project being initially based at the Department of Commerce before moving to the U.S. Department of Transportation from April 1967. Development of the pioneer American high-speed train project would be the culmination of several major players, starting with the Commerce Department and later DOT, as the primary instigators and partial financiers, who would contribute $11.5 million to the scheme, while the Pennsylvania Railroad, which owned the trackage to the Northeast Corridor and was the largest American passenger rail carrier, agreed to contribute $44.5 million. The The other major players in the scheme were those parties awarded a contract of $21 million to deliver the project: the Budd Company, General Electric, and Westinghouse, while Lewis T. Klauder and Associates, a consultant firm populated by rail industry veterans, developed the specifications which were used to inform what would become the as-yet unnamed HSR sets. In total, the Budd Company, as the primary firm that would assemble and commission the HSR sets, was awarded $26 million during 1966 from the Pennsylvania Railroad to deliver 61 self-propelled electric passenger cars that could reach speeds of up to 160 miles an hour, thereby opening up a brand new high-speed corridor between New York and Washington, D.C., this service to be christened the name Metroliner. For the government, the HSR project would be a significant factor in the future industrial development policies of the state with regard to transportation, the main goals of the scheme being to divert travelers from congested airports and highways, reduce fuel consumption, and to improve air quality, while also encouraging economic stimulation via new jobs for the construction and operation of the system. For Budd, whose rail operations were centered in the Red Line plant in Philadelphia, the program potentially offered a significant anchoring system to sustain its manufacturing capacity in the longer term, with the fate of the company being important on both a regional and national level due to Philadelphia's status as one of America's industrial hearts, with railway vehicle construction being one of its primary sectors. The Budd Company was one of America's most prominent railway manufacturers, having first entered the market for train vehicle construction during the 1930s, with its crowning achievement being the creation of the first all-stainless steel vehicle in 1934 in the form of the Pioneer Zephyr, a huge commercial success that gained an international reputation, most notably in Japan. In developing high-speed bullet trains for their Shinkansen line, Japanese National Railways entered into a technical agreement with Budd from 1958 to 1985, which included technology transfer for the design of stainless steel vehicles, as well as technologies related to plastic working, welding, and quality assurance, with stainless steel railway vehicles ultimately accounting for 3/5 of Japan's fleet. Therefore, Budd, on paper, appeared to be by far the most appropriate choice for the development of the Metroliner trains when it came to a domestic American rail equipment manufacturer, with choices from overseas being immediately dropped as early specification work began on what would be the most advanced express passenger train in the United States. The general underpinnings of the Budd Metroliner would come about through a series of compromises between the Pennsylvania Railroad and the Department of Transport, with both bodies, through the medium of Lewis T. Klauder and Associates, setting specifications as to what the resultant high-speed train would look like. The first matter was the proposed top speed, with the Pennsylvania Railroad stating that it should travel at 125 miles an hour in order to exceed the existing 100-mile-an-hour top speed of their GG1 electric locomotives, while the DOT, seeking to create a train that was ostensibly competitive with the Shinkansen in terms of image, demanded 150 to 160 miles an hour for the upcoming units, the higher speed eventually being chosen. Next came the design of the body shells, with the Pennsylvania wanting single-car units with cabs at both ends that could allow for maximum flexibility when it came to formation changes, while the DOT desired 4-car fixed-rake sets with 2 cab cars and 2 trailer coaches, a compromise eventually being reached that each Metroliner unit would be formed of 2-car sets with extendable nose-mounted gangways to connect each individual unit. In the end, the order for the Metroliner units would comprise 20 coaches fitted with Westinghouse propulsion systems, alongside 20 stack bar coaches and 10 parlor cars fitted with General Electric propulsion systems, with Pennsylvania Governor William Scranton announcing plans to purchase 11 additional rail cars for upgraded 80-mile-an-hour services between Philadelphia and Harrisburg, and would be ordered through Philadelphia Commuter Agency SEPTA, as the state was not permitted to contract directly with the Pennsylvania Railroad. The state, SEPTA, and the PRR would eventually reach an agreement on November 3, 1966 for these regional units that amounted to $2 million being contributed by SEPTA and the state government of Pennsylvania, this being funded mostly by mass transit grants from the newly formed Department of Housing and Urban Development, while the Pennsylvania Railroad would receive a free 15-year lease of the cars. However, the Pennsylvania Railroad would withdraw from this aspect of the project soon afterwards, following complaints from the Red Arrow Lines and Capital Trailways bus companies, which operated non-subsidized services in competition with the railroad, with the HUD grants being later found not to be applicable to intercity service, though the order was still placed regardless. Problems, though, were quick to emerge as the Metroliner design moved into the prototype stage, as while the company had previously provided vital input into the Shinkansen project, the domestic and international contributions of the company had essentially not progressed since the last of the Zephyr units had been delivered prior to World War II, the company focusing instead on carriage construction, as the railway industry of the United States faced its precipitous post-war decline. In terms of technological advances, Budd's research and development departments have been focused on three primary projects: disc brakes for freight cars, air spring suspension for coaches, and the RDC multiple units of 1949. While despite the company priding itself on the creation of lightweight vehicles, the average car weight of Budd's products far exceeded that of any equivalent high-speed train. In this regard, Budd had little to no experience when it came to building a true lightweight carriage, such as which would be the linchpin of a successful high-speed rail vehicle, a lower weight meaning a higher speed could be attained by the train, while not requiring inefficient levels of power to be input into the vehicle in order for it to accelerate. This lack of experience in lightweight car construction was one noted by the famously conservative Pennsylvania Railroad management, who had their doubts as to the company's ability to deliver a competitive high-speed train, compounded further by the limited supply capacities in Budd's manufacturing shops during the mid-1960s, caused by the amount of business the firm was receiving at that time, which also constrained its ability to service demand. Another problem was that Budd, desperate to win the HSR project, heavily underbid its contracts, thus creating further financial pressure when delivering the train, though the most egregious concern for the Budd company was its overall lack of innovation and inability to work with the complex electronic systems that were now becoming commonplace across the American transport scene. Having won the new government contract, Budd was required to undertake serious advances in its current technological prowess in order to meet the demands of the HSR scheme, perhaps the biggest leap in the company's innovative portfolio since the iconic Pioneer Zephyr sets of the 1930s, which itself was a major step forward in technology from the builder's previous remit of motorcar assembly, railway carriage work, and a brief stint in aircraft experiments. For the development of the HSR, the complexities of traditional car body assembly and design had been superseded by the need to fit new train car models with cutting-edge microelectronics, a system of operation that was still largely unknown territory, but was essential to ensure that the upcoming electric sets would be capable of achieving their 160-mile-an-hour top speed efficiently. Transistors and amplifiers emerged as the primary spearhead of microelectronics technology during the 1960s, replacing cumbersome mechanical relays and energy-consuming valves respectively, though these new forms of control, still very much in the youth of their existence, required railway companies to rise to the challenge of installing such facets into the systems of their railway vehicles, a far cry from the comparatively simplistic mechanical steam engine. Therefore, in order to assist in Budd's implementation of this cutting-edge technology into the HSR multiple units, a premium would be placed on new financing, innovation, and industrial coordination, an indirect result of which was a new industrial policy emerging, wherein economic support was provided, but government political risks were reduced, with companies such as Budd relying on resource transfers from sectors such as aerospace, auto, and defense via economies of scope. This lack of innovation capacities would ultimately lose Budd millions of dollars, as staff and engineers were trained to use the latest technology in the marketplace without having sufficient background knowledge as to their correct implementation aboard electric multiple units, with pneumatic and electrical systems of this caliber being a completely alien concept to the designers at the Red Line plant. Nevertheless, Budd achieved some success in systems integration by developing 4 test cars for the Northeast Corridor, dubbed T1 to T4, which ran on a test track in New Jersey during the autumn of 1966, with each of these rail cars being developed to measure individual aspects of the train's mechanical and electronic operation. T1 would be used to measure and record the interaction between the pantograph and the catenary at high speed, T2 would measure the track geometry, T3 would provide enough power to meet the performance requirements, and T4 would measure truck performance and ride quality, the testing of these cars being a valuable step forward in terms of track geometry measurement and the study of pantograph catenary interaction. However, The T1 to T4 test cars also had their limitations that meant they were not completely viable in setting the standard for the production models, each of these cars having been converted from regular commuter vehicles and thus did not have the highly complex control systems that were to be used in the eventual fleet coaches. Therefore, the T1 to T4 were largely considered by the Budd engineering team as no prototype of the eventual Metroliner trains, but more demonstrator units that could prove their ability to attain a top speed of 150 miles an hour while running on the 21-mile test track, with hundreds of changes being required between the test cars and the production vehicles through meetings between Budd, the government, the Pennsylvania Railroad, and its major suppliers. In the end, the Budd Metroliner cars that would result were perhaps the most complex self-propelled vehicles ever developed in the United States to that point, but due to Budd's failure to create prototypes that were generally comparable to the eventual production versions, the outcomes of the tests conducted during 1966 gave little to no impression as to how the final sets would perform in mainline service. Each Metroliner set would comprise approximately 3,000 electronic components that were extremely maintenance-heavy, with the design requiring increased pantograph contacts with the catenary and close spacing of these contacts, which created difficulties in maintaining good electrical current collection at higher speeds, with the associated wiring system compounding wider integration challenges. Budd's haste to develop prototypes that were but a fraction of the eventual product was somewhat endemic of the builder's declining fortunes in the railcar industry at the time of the Metroliner project, as while the company was able to garner stainless steel assembly business elsewhere, the collapse of the rail market during the post-war era robbed the firm of one of its primary sources of income, as railroads had not the capital to order new coaching design. Furthermore, Budd did not produce locomotives, while the Metroliner contract did not generate any export orders, which itself is a key part of the commercial success for a high-speed train vehicle design, as per the later French TGV, the German ICE, Italian Pendolino, and various Japanese bullet train models. Nevertheless, with the T1 to T4 prototypes demonstrating an absolute top speed of 156 miles an hour during tests in April 1967, progression of the production Metroliners could begin in earnest, these new rail cars having high-floor boarding, with only one door on each car able to serve low platforms, these trains being among the first high-floor-only rail cars in mainline service in the United States. Development of the Metroliner units was done at an incredible pace, primarily due to the demands of the state to reach the same level as the Shinkansen in terms of performance in a fraction of the time, with Budd and its suppliers being kept to exceptionally strict deadlines that required cut corners or technical development that was nowhere near perfected by the time of its implementation, while French and Japanese engineers enjoyed the luxury of having up to a decade to test multiple prototypes of their HSR projects. Initially, the team behind the Metroliner project were held to a delivery date of 1968 in order for the HSR scheme to be used as a major political topic by the Johnson administration during that year's election, though once Johnson had opted not to stand for re-election as President of the United States due to increasing opposition to the war in Vietnam, the timescale was lengthened marginally, but deadlines kept unsympathetically tight. Regardless, in May 1967, an initial service date of October 29th of that year was announced, followed a month later by the official adoption of the Metroliner moniker for the trains and their services, with the first complete unit being displayed at the Red Line factory in July 1967, only 13 months after the initial order had been placed under the high-speed ground transportation project. The first Westinghouse-powered Metroliners were delivered to the testing location at Jenkintown Station in the Philadelphia suburbs in September 1967, and immediately began testing on the Reading Company's West Trenton line, though from the start these units suffered multiple failures of the control and propulsion systems at just 70 miles an hour, and the Pennsylvania Railroad called for the proposed October 1967 introduction of the sets to be delayed. Thus, January 1, 1968 would be the new service entry deadline for the Metroliner project, and the first two cars began testing on the Pennsylvania's main line on November 18th, the initial mechanical and technical gremlins being ironed out to the point that the sets could achieve 125 miles an hour, with one example even being pushed to 164 miles an hour near Princeton Junction in New Jersey 6 days later. However, testing also revealed that the cars would not be able to operate anywhere near that speed in revenue service, primarily due to the phenomenal power draw of the Metroliner units when running at speeds over 140 miles an hour, the biggest problem overlooked by the designers being the fact that the state-of-the-art technology proposed for the Metroliner had to be operated on infrastructure that was built in the 1930s. By the late 1960s, the electrical infrastructure of the Pennsylvania's main line from New York to Washington, D.C. was largely unchanged from when it had been originally erected in 1935, with the overhead wiring, together with substations, being designed only to accommodate the comparatively simplistic GG1s of that era, rather than the power-hungry Metroliner sets that were at the cutting edge of railway technology for the United States. On December 17, 1967, the Metroliner's ability to run at full speed was dealt another blow when these high-speed train sets came into contact with the Pennsylvania's MP-54 electric rail cars from 1915, when due to the pressure drop between a 130-mile-an-hour Metroliner set and an MP-54, resulted in the latter's windows being ripped out, meaning the new trains would be forced to sacrifice their speed advantage in favor of working around the older multiple units. On February 1, 1968, in a bid to save itself from imminent collapse, the Pennsylvania Railroad chose to pool its capital with another major railway firm in order to keep both companies afloat, its partner being long-standing rival, the New York Central, thus creating the Penn Central Transportation Company, a hopelessly flawed amalgamation of railroad businesses that did little to complement each other and would ultimately fail to achieve widespread cooperation. With no work being done to improve the existing situation in the passenger sector, as the Penn Central's management continued to perceive itself as two separate railroad companies, the firm would find itself losing $100 million per year on passenger services by the end of 1968, with no clear direction in sight. For the testing of the Metroliners, this continued with ongoing flaws well into 1968, a major issue with the scheme being the problematic partnering of Budd with General Electric and Westinghouse, as the government's rationale in marrying these three firms together in the project were potential assurances that there would be two viable suppliers going forward. Budd, through their previous record of working alongside General Electric or Westinghouse to provide propulsion systems for their vehicles, were confident that these two suppliers could present technology that would perform without fault as it had done before, regardless of the fact that both companies were just as inexperienced with the technology as Budd was. As an example, the Metroliner cars fitted with the Westinghouse propulsion system represented one of the first applications of phase control thyristor propulsion systems, but this created problems of electrical interference with the control circuits of the thyristors, combined with a poor initial pantograph design that would bounce along the aging 1930s catenary and often brought down the wires. Thus, the Westinghouse cars, once this fault had been discovered, were withdrawn from testing as the supplier worked to redesign the circuits at their Pittsburgh facility, while from March 2, 1968, the first cars fitted with General Electric propulsion systems were delivered for testing and presented a superior pantograph design that successfully overcame the bouncing issue against the wires. However, the General Electric units were also riddled with major problems with the design and build of their components, though not ones identical to those experienced by Westinghouse, the outcome being that Budd was chained by contract to two component suppliers who had barely the experience necessary to develop a fully functional propulsion system. In light of the cumulative problems with the Metroliners, and with these machines being no closer to completion than they had been 6 months prior, March 12, 1968 would see the service entry for these trains delayed indefinitely, followed by testing being fully suspended from June 24 to mid-July of the same year, with 6-car test trains demonstrating severe issues with electrical arcing. Finally, after months of work resolving the issue of the General Electric and Westinghouse-propelled cars failing to work together properly, the first test train using these propulsion systems in combination undertook its maiden run on August 8, 1968, while June 1968 had seen an agreement reached between the State Transportation Assistance Authority and Penn Central for a combined $4.5 million order for 11 Metroliners for the Harrisburg service. The remainder of 1968 was spent overhauling and preparing the Metroliner and the main line for their service entry, with demonstration runs for officials being conducted in 4-car formation throughout the summer, while substation modifications were carried out during the autumn in order to ensure the infrastructure was capable of handling the Metroliner units up to 135 miles an hour. In early October, Several test trains proved the viability of the planned sub-3-hour schedules for Metroliner diagrams between Washington, Baltimore, Philadelphia, and New York, and a legal settlement between Budd and Penn Central was thus made in November 1968 for the handover of the units for service entry, December 20th seeing the railroad company announce January 16, 1969, as the start of Metroliners in public use. The day prior to public service entry, a Washington to New York round trip for VIPs was operated on January 15, 1969, with the initial schedule for regular operations seeing a single daily round trip leaving New York in the morning and Washington in the afternoon, the original one-way fare for the service being $12.75 in coach class and $19.90 in first class, or $107 and $168 in 2024 respectively. However, due to numerous circuit breaker trips and catenary outages, the proposed use of 8 coaches on rush-hour trains was scaled back to 6 cars that comprised 2 club cars and 4 snack bar coaches, while MP54s on Washington to Baltimore commuter services still had their windows sucked out by passing Metroliners. Metroliners were also tested during February 1969 on the main line north of New York to the then extent of the wires at New Haven, Connecticut, though these trains once again led to power drops due to the aged overhead wiring of the route, the General Electric cars showing the greatest promise in terms of reliability, while Westinghouse-fitted coaches still saw electrical issues that resulted in their storage at Trenton awaiting rectification. As more cars were brought into use, the service patterns gradually increased, including a non-stop round trip on a 2.5-hour schedule, which was added from April 2, 1969, and from mid-August, the first Westinghouse coaches were brought into regular use and tested up to 160 miles an hour, though during the same year, the maximum speed of the Metroliners was temporarily dropped from 120 miles an hour to 110 miles an hour due to ongoing power issues. Eventually, due to the condition of the track and signaling system, the Federal Railroad Administration never allowed Metroliners to go faster than 120 miles an hour between Washington and New York, regardless of the incredibly favorable profile and general track layout of the Northeast Corridor, including long sections of straight track in New Jersey and numerous 4-track stretches that could sideline freighter commuter trains. Nevertheless, the Budd Metroliner was still by far the fastest passenger train in North America, providing speed, comfort, and amenities that could easily compete with domestic airlines, including Eastern's famous shuttle service between New York and Washington, with half of Metroliner passengers, within 2 years of service entry, having switched from other modes, while 70% of customers were men on business trips, the average cost per car mile for Metroliner sets being 77 cents to maintain. From February 25, 1970, the 11 Westinghouse-powered cars intended for the Harrisburg service completed their performance testing, but the Penn Central refused to accept these cars due to numerous technical issues and their general unsuitability for the service, presenting slower acceleration than the current fleet of Silverliner commuter units, while also suffering from overheating problems due to their frequent stops, and had difficulty climbing the grade out of suburban station. Additionally, the corridor lacked high-level platforms to effectively use the cars, and 15 substations would require expensive modifications, thus leading to these 11 coaches being placed into storage before being leased by the Penn Central to help bolster the mainline New York to Washington run, these being dispatched to Budd for modifications in April, while the Harrisburg corridor would instead see an investment of $100,000 to upgrade Silverliner sets. Though the Budd Metroliner was settling nicely into its new role as the premier high-speed train for the United States, the continued reliability problems, even as new sets continued to come online, meant the DOT and Penn Central, from May 1970, began early arrangements to modify one car of each propulsion type to try and iron out these ongoing issues, with out-of-service rates reaching 40% and higher within the first 18 months of operation. In June, Senator Clifford Case of New Jersey began pushing the DOT to devote $5 million towards the Metroliner rebuilding program in order to increase reliability, with an official 2-year demonstration program beginning from October 1, 1970, a feasibility study of upgrading the cars for higher sustained speeds being initiated, all while the top speed of the service sets was reduced further to 100 miles an hour from February 1971 due to wear on the equipment and infrastructure. On May 1, 1971, In order to try and save the ever-deteriorating American rail passenger market through direct state funding, the Nixon administration established the government-owned National Railroad Passenger Corporation as marketed under the name Amtrak, and would take over the loss-making intercity passenger rail services from the Penn Central and the other private railroads. Thus, 49 initial Metroliner sets were leased from Penn Central through a reimbursement by Amtrak, followed in September by the leasing of the remaining 12 sets that had yet to be commissioned by Budd at their Red Line plant, all while the DOT, in contract with General Electric and Westinghouse, commissioned further research into electrical modifications for the train sets during June 1971, with detailed plans made a month later. By November, Metroliner services were operating 12 daily round trips, including some trains that continued to New Haven, but a permanent 100-mile-an-hour speed restriction on the units was maintained, which meant they were no better than the near 40-year-old GG1s they were intending to replace, with Amtrak considering deactivating the Metroliners and simply having them loco-hauled by GG1s on corridor trains during early 1972. However, as the cars were the only new rolling stock in Amtrak's possession, it was decided to continue efforts to increase their operating reliability instead, and from February 1972, one GE-powered car was shipped to Erie, Pennsylvania for the DOT-funded rebuilding program, with the intention being to modify all cars by 1976, this being followed by the first Westinghouse-powered car in March of the same year. In late April, Amtrak accepted 6 of the leased cars for revenue service, while the first 2 rebuilt cars emerged from Erie in November of that year, with the remediation work including the dynamic braking resistors and the air intakes being relocated to a streamlined bump on the roof, reducing overheating and snow ingestion issues that had occurred when they were mounted under the car body. The rebuilt cars had a maximum speed of 130 miles an hour, while following the completion of 2 further cars in February 1974, testing of a full 4-car set up to 150 miles an hour was achieved during May, prior to their return to public use in July, this rebuilding program being largely successful with the exception of continued rough riding concerns, and the fact that the program itself cost $500,000 per car, $100,000 more than it cost to build them originally. Amtrak pressed on with this work to see the Metroliners modified as per the original test cars, with units that had logged over 11 million miles in revenue service being prioritized, though in the end, few cars were actually repaired, and by 1975 the out-of-service rate was still sitting at an alarming 27.5%, with sets often running short of available cars during periods of highest demand. This led, from February 1976, to Amtrak cutting Metroliner diagrams from 15 to 13 round trips per day due to the lack of serviceable cars, while from April 1st of the same year, the bankrupt Penn Central, along with a slew of additional failed railroad companies, were nationalized by the Ford administration into Conrail, and thus the existing leasing agreements on the Metroliner trains was passed over to this new company. With the Metroliner project having been an overall failure for Amtrak, the company sought various means of replacing these troublesome multiple units, starting with the General Electric E60 locomotives of 1974, which were derived from an existing design for freight engines built by the Black Mesa and Lake Powell Railroad of Arizona, though these proved to be completely ill-suited for high-speed passenger work and were speed-restricted following a series of derailments. From 1976, Amtrak looked to foreign suppliers as a means of providing a lightweight electric locomotive for Metroliner diagrams, the result being the testing of a Swedish SJ AW1 RC4 and a French SNCF class CC 21000 locomotive on the Northeast Corridor, with the RC4 proving to be the superior design and would thus lend itself to an American-built variant capable of 125 miles an hour. At the same time, Amtrak considered a potential new fleet of Metroliner units dubbed the Metroliner 2, which would be heavily modified to iron out the faults of the originals, 118 cars initially being ordered, but this was soon cut back to 50 and later fully cancelled, all while on-time performance for the Metroliner fleet fell from 81% to 46% throughout 1976. In the face of this falling performance, consultant Louis T. Clauder and Associates was commissioned during November 1976 to provide a report on the future of the Metroliner trains, with this report highlighting that the rebuilt cars had half the maintenance costs of the originals, and recommended an aggressive overhaul program to be initiated, with Amtrak announcing on February 6, 1977, that $24.4 million would be spent on overhauling all 61 cars as part of a larger fleet renewal program. This led, on September 28, 1977, to an order for 8 of the American-built RC-4 locomotives dubbed the AEM-7, while 16 Metroliners would be overhauled, Amtrak releasing a specification for overhauling the 57 unmodified cars and awarded a $20 million overhaul contract to General Electric during November, the first unit being dispatched to GE for overhaul in March 1978, while GG1s hauling coaching stock and regeared to 110-mile-an-hour operation would cover the shortfall on a slower schedule. On April 30, 1978, the once 2.5-hour schedule was increased to 3 hours and 20 minutes as more loco-haul diagrams were introduced to cover for the out-of-service Metroliners, while the first rebuilt cars entered service on May 17, 1979, the overall Metroliner scheduling layout by July 1979 being 3 round trips operated by rebuilt cars, 4 by unrebuilt cars, and 4 by loco-hauled trains. By January 1980, rebuilds covered 6 of 14 daily round trips, followed during the middle of the year by the first AEM-7 locomotives coming online, this new traction easily demonstrating that it could match Metroliner diagrams while delivering reliability that was far in excess of the multiple units, their arrival allowing for an increase in daily round trips from 12 to 14 by October 1980, while the most unreliable Metroliners were taken offline. The transfer from multiple units back to loco-hauled operation was quick, and from the first arrival of the AEM-7s in mid-1980, the last unrebuilt Metroliner units were taken out of service on April 1, 1981, followed by the venerable GG1s in May, and finally the very last of the Budd Metroliner units on October 23, leaving the future of mainline traction between Washington, D.C. and New York in the hands of AEM-7s and speed-restricted E-60s. Some survivors would continue to see work on the Harrisburg corridor going into the mid-1980s, these Metroliner units being renamed Capital Liners, and would work between New York and Harrisburg on the Keystone service, usually in 3-car formations, though once again, the reliability concerns that had doomed their original introduction on this route under the Penn Central in 1970 came to light, and from January 1988, all sets would be loco-hauled. Ultimately, the Budd Metroliners withdrawn from use were found to be much better performing as coaching stock, and throughout the late 1980s and into the early 1990s, the survivors were stripped of their running gear and put to work as push-pull cab control cars across various corridors, a task that they still perform to this day on services such as the Keystone Service, Valley Flyer, and Hartford Line, though new coaches from Siemens intend to see these retired from 2025. However, though the Budd Metroliner units were an overall failure and never met the targets they were hoping to achieve, their sturdy and comfortable body shell design was generally praised, and during 1975, Amtrak would order a fleet of 492 Amfleet 1 cars based on the Budd Metroliner's shell at a cost of $192 million, this being followed in 1980 by an order for 150 Amfleet 2 cars at $150 million, the Amfleet becoming the backbone of Amtrak's operations across the continental United States. Another application for the Metroliner's body shell came with the SPV 2000, as announced in 1976, which would comprise single-car diesel multiple units that would replace the older RDC coaches of the 1940s and 50s, being powered by 360 horsepower General Motors diesel engines and being capable of a top speed of 120 miles an hour, the SPV 2000 being designated for both regional commuter and intercity services across America. The SPV 2000 prototype began testing in Pennsylvania on December 8, 1977, with the state of Connecticut placing the first order 9 months later for use on the Danbury branch, while the other 12 units would be leased to Amtrak to replace their RDCs between New Haven and Springfield, Massachusetts, with 50 Con-Dot units entering service from April 23, 1980. Sadly, much like the Budd Metroliners, the SPV 2000s would again suffer a myriad of problems with regard to their traction equipment, specifically due to the dedication of 2 8-cylinder engines solely to propulsion, while the lighting, air conditioning, control voltages, and other ancillary loads were handled by a separate 4-cylinder power unit built by Perkins, which was provided an insufficient cooling radiator that was often clogged with leaf debris. The result was that the Perkins unit would routinely overheat due to debris ingress, thus meaning that control of the unit's functions beyond propulsion was lost, thus rendering the car inoperable, while the general design, including suspension and body shell, was completely over-designed for the role it was intending to fill, the 120-mile-an-hour top speed being highly optimistic in consideration of the SPV 2000's general employment on winding regional branch lines. Thus, the SPV 2000 proved to be another major failure for the Budd Company, and its attempts to branch out the Metroliner design to other potential uses beyond a non-powered passenger coach, the SPV 2000 spending a majority of their careers being hauled by locomotives before falling out of use by the middle of the 2010s. In the end, the failure of the Budd Metroliner project came down to the fact that high-speed rail in the United States was of a lower priority when compared to international equivalents, with Japan having invested vast sums of state funding into the Shinkansen as a means to ensure economic growth going into the 1970s, while France had centralized government control over the transportation system and could thus inject funds where appropriate for schemes such as the TGV. By contrast, the priority of the American government was military-industrial policy due to the ongoing Vietnam War, with the 4 years of development for the Budd Metroliner scheme, 1966 to 1970, seeing federal expenditures for Defense Department research and development total $30.7 billion. Furthermore, research and development investments by railroads for their passenger operations were either too limited in scale or too remote to help sustain Budd as a rail manufacturer, with the period between 1950 and 1960 seeing the total net investment by the railroads in road and equipment property by classes 1 and 2 line haul railroads and leases standing at $6.9 billion. During 1961, a study noted that the railroads made $14 billion in new capital improvements after the end of World War II, with productivity increases being driven by research projects that included a rail laboratory and research center, which worked on various projects including continuous welded rail and alloys for lightweight car construction, or areas of technology synergy between freight and passenger services. While some post-war innovations were explicitly aimed at passenger service, in general, the railroads experienced a long hiatus in research and development within this field, which made it difficult to assimilate the advanced technology of the 1960s and 70s into underpinnings that had not evolved since before World War II, with major rail producers, in the face of an increasingly bleak market for passenger trains, doing little to modernize their pre-war designs. At most, the last major investments in passenger rail equipment came during the late 1940s and early 1950s, though this was primarily targeted at low-capacity long-distance coaches that were aimed at a market where the railroads were losing out most significantly against domestic airlines, thus rendering this new rolling stock obsolete almost immediately after their entry into service. By 1967, the Pennsylvania Railroad was losing 24 cents on every dollar received from passenger tickets, and with its significant investments in new passenger equipment and existing infrastructure, such as the magnificent Penn Station in Manhattan, alongside the catastrophic collapse in both passenger and freight demand on the railways, the company was being bled dry at an alarming rate. This extreme lack of harmony within the primary railroad company backing the Metroliner project, combined with an apparent failure to invest in new technology on an industry scale within the United States, meant Budd was forced to rely heavily on external suppliers to provide the latest electronics and mechanics to help get the new train running, these outside sources ultimately grabbing a greater share of profit from Budd. From Budd's once simple but sturdy ability to provide mainline long-haul passenger equipment, with a majority of the costs being represented by the company's own design, manufacturing, and assembly operations, the firm's dependence on external suppliers for electrical components and sub-assemblies meant this amounted to over 70% of the total costs of the self-propelled transit cars and commuter cars by the late 1960s. These developments meant the company's design, engineering, and tooling costs had to be paid off by just 30% of each unit cost, while at the same time making Budd vulnerable to disruptions from its suppliers, as was the case with General Electric, which suffered a strike during 1970 that delayed railcar production. While the Budd Metroliner project should have been the high commission government-backed scheme that all major railway builders hoped they would win, The reality was that the culmination of factors, including limited R&D investment by the railroads over the previous decades, an inability to keep up with the demands of the latest technology, and the fact that this all had to be delivered within half a decade, nearly pushed Budd to exit the railroad business altogether. With sales in the railway division of Budd having fluctuated from only 1 to 13% of the company's total annual sales during the period between 1966 and 1969, a strong consideration was for the firm to instead focus on supplying the ever-expanding automobile business, added to further by Budd's later rectification works on the Metroliner sets after delivery, which amounted to $26 million, amounting to a total overall loss of $20 million on the entire scheme. Budd's two suppliers also suffered by not having a sufficient supporting R&D program to launch a new generation of systems, though while Budd, amid talk of their never taking on the role of a primary contractor for a railroad project ever again, ultimately did not exit the railway business, though the fact that they made public motions as to doing so was a clear sign of how unsustainable this market sector was viewed. In truth, Budd's calamitous development of the Metroliner was essentially an outcome of the American indirect industrial policy that was aimed primarily at providing a transportation service rather than sufficiently funding railcar producers at the scale necessary for entering a new production paradigm, with Congress opting for a free market orientation rather than the more state interventionist countries such as France. The main objective of the Metroliner program was to prevent the total demise of passenger rail by providing service that was only marginally faster than the existing rolling stock, with the entire project being more a demonstration rather than a fully committed effort by Washington to redress the balance of the transport sector, and with its limited geographical and time horizon, did not warrant significant government investment. This overarching hesitancy to provide substantial government R&D program support for the passenger rail industry meant financing for the railroad was primarily private, with the exception of funds being injected for safety-related schemes. The Federal Railroad Administration, created in 1966, supporting improvements in passenger trains, but had no long-term programs due to the small scale of the market and the lack of political will to push for such projects. A testament to this imbalance of state funds into a project that was ostensibly of national importance came in the fact that the Budd Company, General Electric, the Pennsylvania Railroad and its successor Penn Central and Westinghouse would spend over $60 million of private funds on the Metroliner, while the government would only provide $12.9 million of public money. This was essentially a tacit admission that the state had no interest in serving passenger rail, demonstrated by the fact that other sectors of the transportation industry were able to garner huge government subsidies during the period between 1961 and 1970, with company-financed R&D investment during 1961 standing at $6.2 million for railroad carriers, $15 million for railroad equipment manufacturers, and $379 million for aircraft and part suppliers. As the decade progressed, by 1962 this would shift by only 0.06% for railroad carriers, 1.7% for railroad suppliers, based on company funds, and 24% for the aircraft and parts manufacturers, with 2.4% company funds and 21.6% government funds, while full-time equivalent R&D scientists and engineers per 1,000 employees were 101 in the aircraft and missile sector, 52 in electrical equipment and communication, 48 in professional and scientific instruments, but only 16 in motor vehicles and other transportation equipment. While indirect industrial policy mostly hurt the American railroads, there was one case wherein the investment of the state into the aerospace industry helped solve a problem with the Budd Metroliner, that being when John Marchetti, a scientist with an electrical background and a figure in the Cold War aviation industry, worked with the Department of Transport to help retrofit the Metroliners once they had entered service. Through his extensive experience, Marchetti was able to identify several key problems with the Metroliner's electronics through test programs that measured and recorded specific performance elements to guide the retrofit program with real-world data, thereby giving the project critical electrical and electronics expertise that was severely lacking within the ranks of Budd, and thus solving many problems the company faced in fulfilling its procurement contract with the government. However, Marchetti's contribution to the Metroliner scheme was very small in the wider context of the entire project, with the general consideration being that had an engineer of his expertise and acumen been employed from the start of the train's development back in 1966, many of the lingering electronic faults could have been rectified, long before the units ever entered public service. Furthermore, while the Metroliner scheme was generally a failure with regards to its inability to provide major improvements to the wider Northeast Corridor, as well as being but a small part of the American passenger rail industry as a whole, its position as the first major innovation in the rail sector that was pushed through to completion since the end of World War II was a significant stimulus for future development of wider projects. It was also instrumental in keeping the Budd Company afloat in the face of falling orders in the passenger rail sector, with its only other sustained work during this period being the delivery of 600 cars for the R32 subway train, as ordered by the New York City Transit Authority in June 1963, these subway trains also being assembled at the Red Line factory alongside the Metroliners. To conclude, the Budd Metroliner was a wrong-headed concept for what the government was hoping to achieve, insisting that a state-of-the-art high-speed express passenger train that could match the performance of the Shinkansen be delivered in as short a time as possible using railway infrastructure that was over 30 years old, while at the same time being built by rail manufacturers with a severe deficit in technological prowess and strangled in terms of funds. As was proven by Europe and Asia in the decades to come, the only way to create a sustainable high-speed railway system would be through the building of dedicated lines segregated from regular commuter and freight services, a matter that could not easily be overcome on the Northeast Corridor due to the expansive urban development that surrounded the course of the route. Therefore, the government was attempting to force a square peg into a round hole when it came to creating the Budd Metroliner, a machine that was far too over-engineered for its own good and should have had technical ambitions that were but a fraction of what Budd, General Electric, and Westinghouse struggled to obtain in the highly constrained schedule of the project, with decades of innovation needing to be learned in the space of only 2 to 4 years. In the end, had the Budd Metroliner simply been built to a more reasonable 125-mile-an-hour top speed, while continuing to maintain the winning body shell design and interior that saw greater use in the non-powered Amfleet cars, then it may have been possible for America's first foray into the realm of high-speed trains to have been a success, and the cornerstone of future projects for the United States going into the 1970s and 80s.